Welcome to MS 100 lesson. This is a continuation lesson for graphical analysis F net equals to MA. So in the first lesson, I was evaluating the relationship between the acceleration of an object and the net force. So we have evaluated that the acceleration of that object or the acceleration of an object is directly proportional to the net force acting on that object, right? And we performed an experiment in such a way that we are changing the net force and we check what will happen to the acceleration of an object. And we concluded that when the net force increases, the acceleration also increases. So there is a direct proportion between the two variables. So from our graph, we can see that this is a linear function. And if it is a linear function, we can perform our graphical analysis. And from our graphical analysis, we have concluded that the gradient of this line is equal to the inverse of the mass, or the gradient is equal to 1 over mass. Okay, so now in this lesson I will be looking at the relationship between the acceleration and the mass of an object graphically. So let's say we have an experiment, right? I'll say that this is experiment number 2. So in this experiment, what we want to do is we want to check the relationship between acceleration in meters per second squared and the mass of an object in kg, right? Provided that we are using a constant net force. So since the net force is constant, right? So that is the controlled variable. So that is the controlled variable in this experiment. And since we are going to be changing the mass of the object, right? Then it means the mass of the object is the independent variable. And we will be checking, or we will be measuring the amount of acceleration that arises from a certain amount of mass. So the acceleration will be the dependent variable, right? So let's say we start with a mass of, for example, if there is no mass, then it means there is no acceleration, there is no object to accelerate, right? So let's say the mass of the object is 2, right? And we measure an acceleration of 10 meters per second squared, right? And then we increase the mass of the object maybe to 4, right? Okay, or maybe to 3. Let's say we increase the mass of the object to 3, and then we measure an acceleration of 6. So we can see that when we increase the mass, right? When we increase the mass, the acceleration decreases, right? But now for the first instant, to say when mass is equal to 0, it does not make sense because there is no object to accelerate. So we will remove that first point, which is 0 is to 0, right? We would start by saying we have a mass of 2 kg and our acceleration we measure 10 meters per second squared. And we increase the mass to 3 kg, the acceleration is 6 meters per second squared. So now let's continue to increase the mass of the object. So when we increase the mass of the object to 4, we find that the acceleration is 2 meters per second squared. All right, so what is the trend between the mass of the object and the acceleration? We can see that when the mass increases, the acceleration decreases, right? Or if the mass increases, then it means the acceleration, when the mass decreases, the acceleration increases if we are going up the table, right? So the conclusion is that the acceleration of an object is inversely proportional to the mass of the object, right? So let us plot a graph from these results. So on our x-axis, we will have the mass of the object in kg, since that is what we are changing. and that is the independent variable, and the dependent variable will be the acceleration in meters per second squared, right? So that is the acceleration versus mass. So for the first point, if I were to use a scale of 2, let's say 1, 2, 3, 4, 5 on the x-axis, and we use a scale of 2, 4, 6, 8, 10 on the y-axis, right? So if we have a mass of 2, we have an acceleration of 10, and that is up there, right? We have an acceleration of 10. And if we have a mass of 3, we have an acceleration of 6. So that is the point there. But if we have a mass of 4, we have an acceleration of 2, right? So that is somewhere there. So if we plot this, we obtain a curve like that, right? So since this is a curve, it's a bit tricky for us to apply our graphical analysis in terms of y equals to mx plus c, right? But this is the relationship that we get between the acceleration and the mass, whereby we have acceleration being inversely proportional to the mass, right? And the type of graph that we get a curved graph like that. So is it possible to apply the graph analysis for y equals to mx plus c? In this case, the answer is no, because this is not a straight line, but it is a curve, right? So how can we make it possible for us to evaluate the relationship between the mass of the object and the acceleration of that object? We convert this graph into a straight line, right? So we take that curve, we convert it into a straight line, so that we can be able to apply y equals to mx plus c. But how do we do such a thing to convert a curve into a straight line? So in this case, we see that we have two variables, right? Whereby we have the mass and the acceleration, and we get a curve like that, right? But for us, in order to get a straight line, one of the variables must be an inverse. So at least one variable must be an inverse, right? So for example, we can have a graph of, say we make acceleration the inverse. That would be 1 over a versus mass of the object. Then now we can obtain a straight line graph, right? Or we can have a graph of 1 over mass versus acceleration. We can also obtain a straight line, right? So one of the variables must be an inverse in order for us to get a straight line, okay? Because the relationship between the acceleration and the mass of the object is an inverse relationship, and we cannot apply our graphical analysis in this case, right? So we convert this into a straight line. When we convert this into a straight line, one of the variables must be an inverse, right? So how do we convert one of the variables into an inverse? So looking at the results that we have obtained in this table, right? We can start by making the mass the inverse of, we can start by making the mass the inverse. So if we make the mass the inverse, that would be 1 over m, which is 1 over kg, right? So instead of 2, then that would be 1 over 2, which is the same as 0.5, okay? And instead of 1 over 3, instead of 3, that would be 1 over 3, and that is 0.33, right? And then instead of 4, then that would be 1 over 4, right? And that would be 0.25, okay? So now we have our mass as an inverse. So if we plot this inverse of the mass versus acceleration, then now we can obtain a straight line, which is this graph over here. The mass is an inverse, okay? Or we can have an inverse of the acceleration, okay? Then that would be 1 over meters per second squared. So instead of 10, that would be 1 over 10, right? Which is 0.1. And instead of 6, that would be 1 over 6, which is 1.67. I mean 0. Sorry about that, 0.167. And then instead of 2, that would be 1 over 2, which is 0.5. So now we can plot the graph of 1 over acceleration versus the mass, right? In this case, the acceleration is an inverse. So that is the sketch that we obtained there. So let us perform our graphical analysis for each case, right? Let's start with this one, whereby our acceleration is the inverse. We want to check what does the gradient represent. So that is our graphical analysis, right? So now we have mass. This side we have 1 over acceleration, right? The mass is in kg, and this side we have 1 over meters per second squared. Then now we obtain a straight line, okay? So let us perform our graphical analysis. So with our graphical analysis, step number 1, we can see that this is a linear function. We say y equals to mx plus c, okay? And then step number 2, we substitute whatever we have on the axis into that y equals to mx plus c. So instead of y, I would insert 1 over a, right? And that m is the mass of the gradient, okay? I mean, that is the m for the gradient, not the mass of the object. And then in the x, we have our mass, which is m, and the value of c, which is our y-intercept, is 0, okay? So for step number 2, we obtain 1 over a equal to the gradient multiplied by the mass, okay? And then step number 3, we manipulate the original formula, and the original formula is F net equals to ma, right? So if we manipulate this formula in such a way that it looks like the formula in step number 2, we have to make 1 over acceleration the subject of the formula, okay? So what we can do is we can divide both sides by acceleration, okay? Then we would have F net equals to F net over a equals to the mass of the object, and we can multiply both sides by 1 over F net, okay? And then we get 1 over acceleration equal to the mass times 1 over F net, right? But if you look at equation in step number 2, the equation in step number 2, it says 1 over a. We also have 1 over a is equal to the gradient times the mass. So the mass is at the end. So we can write this as 1 over a is equals to 1 over F net times the mass at the end, okay? So step number 4, we compare the two. So in step number 2, the formula that we have obtained 1 over acceleration is equals to the gradient of the graph multiplied by the mass of the object. And then in step number 3, we have obtained 1 over a equals to 1 over F net, which is the formula down there, times the mass. So now let's compare. We have 1 over acceleration, we have the mass of the object, and now we have the gradient being 1 over F net. So now we know that the gradient of the graph is the inverse of the net force, okay? So if we want to calculate the net force that was being applied in this experiment. We have to calculate the gradient first by choosing 2 points on the graph, and then we insert our gradient there, or we substitute our gradient there, then we solve for our fnet, right? So that is the graphical analysis for 1 over a versus mass of an object. Okay, so that is the graphical analysis for this sketch. One must be an inverse, the acceleration was the inverse, and we have obtained that the gradient of this graph is equal to the inverse of the net force. So let us do the graphical analysis for the second one, whereby we have acceleration and the inverse of the mass on the x-axis. Okay, so now we have acceleration and the inverse of mass, and in this case, since one is an inverse, we obtain a straight line graph, right? So now our graph analysis, step number one, we can see that this is a straight line, then y is equal to mx plus c, right? And then step number two, we substitute the values that we have on our graph. We have acceleration on the y, and that m is m for the gradient, not for the mass. And on the x, we have 1 over mass. The value of c, which is our y-intercept, is 0. Right? So we obtain an equation of the acceleration is equal to the gradient times 1 over mass. Right? And then now we go to the original formula, which is step number 3. We manipulate the original formula in such a way that it looks like the one in equation 2. Okay, so in this case, the acceleration is the subject of the formula, so we would manipulate this. We would divide by mass both sides, and then we get acceleration is equal to fnet divided by the mass of the object, right? But looking at the formula in step number 2, we have 1 over the mass at the end, so we can write that as, so that can be written as A is equal to the net force and 1 over m at the end. And then step number 4, we compare, right? So let's compare the formula in step number 2 and step number 3. Step number 2, we have acceleration equal to the gradient times 1 over m, and then the last one, we have acceleration is equal to the net force times 1 over m. So if we can compare, we have our acceleration, we have our 1 over mass, and now the gradient represents the net force. Okay, so it means the gradient is equal to the net force. So if you want to obtain the net force now, you just have to calculate the gradient, and that gradient is your net force in newtons. Okay, so the gradient in this case is equal to the net force. But for this one, the gradient is equal to 1 over the net force.